An interesting result is obtained if one plots the binding energy per nucleon as a function of nucleon number, or mass number. We'll look at the curve on the next slide. But this curve peaks at around iron 56, although there is new research that suggests that the peak is actually at nickel 62. There is structure in the curve below that mark due to the energy levels of the different nuclei. Helium-4, for example, has a relatively high binding energy per nucleon, indicating that it is very stable compared to its neighboring nuclei. Nuclear binding energies are on the order of 1 million times greater than that of electron binding energies. And that's why nuclear reactions involve so much more energy than chemical reactions. Here's our plot of average binding energy per nucleon as a function of numbers of nucleons in the nucleus. And as you can see, just to bring to your attention again, you can see this peak here for helium-4 showing how high the binding energy is relative to everything around it and showing its stability. We see similar peaks here at carbon-12 and oxygen-16. The maximum binding energy per nucleon occurs here, which is identified as iron 56. And as you can see, it slowly tails off as we go higher and higher up the periodic chart. When you look at the curve of binding energies versus atomic mass numbers, the elements to the left of iron 56 are the result of stellar fusion, the reaction which combines nuclei to form the nucleus. And we'll discuss those in more detail later. These reactions release more energy than is put in to get them to occur, and that's what causes the sun or stars in general to shine. Elements to the right of iron 56 cannot be created that way. They require vastly more amounts of energy and only occur in the last stage of a star when it explodes.